Okay, great. Well, good evening, everybody. I'm Steve Floyd, W4YHD. I've been a licensed and active ham since I was 12 years old. I'm a professional electrical engineer, bachelor's and double E from Virginia Tech, where I was also the chief engineer of the student radio station, WUVT FM, and a DJ there during my time, and with the Ham Club, K4KDJ. Then I went to Johns Hopkins University, got a master's in double E with an emphasis in radar engineering and RF and microwave engineering. And I'm going to tell you the story of HAARP because I've been the chief designer, chief engineer of HAARP. So doesn't it just figure that a ham would take on such a big project? Okay, so let's see here. What is the current status of HAARP? Well, the site construction was completed in 2007 for full power operations, which we'll talk about in depth. The program and site shut down in June 2013 due to politics of money. You may have heard that HAARP was shut down for a short period. It was only 9 months. But due to these nasty sequestration budget cuts that kicked in because our two political parties couldn't agree on a budget, DoD took a 20% budget cut, and many R&D projects were canceled. The HAARP O&M contract came up for renewal in June of 2013. They did not renew because they did not have money, and thus it was shut down for only 9 months, and then it came right back with funding and then was taken over by the University of Alaska. So it was only shut down for a short period. Very unfortunate. The HAARP program and site restarted 9 months later in 2014 with DARPA funding. The University of Alaska out of Fairbanks, the Geophysical Institute, took over the HAARP program and all facility operations in 2015, and that continues to this day. The HAARP program has remained in full operation with 3 to 5 major research campaigns per year. We'll talk about that. We are installing new equipment, and latest is a new high-power laser-based radar called a LiDAR, which gives us new diagnostic capabilities. And sorry, all, and I do mean all, of the HAARP conspiracy theories out there are completely false and quite ridiculous. Okay, HAARP is a joint program with the Air Force, Navy, and DARPA, DARPA being the Defense Advanced Research Projects Agency. And it's currently operated by the University of Alaska out of the Fairbanks campus, the Geophysical Institute, it's called. And it's radio science research in Alaska. And there's a sunset picture of the HF transmitting array, which is only one of many instruments at the site. And we'll talk in great depth about this. So why is HAARP important? Well, it's the USA's only state-of-the-art radio science research facility with premier technical capabilities from ELF, extremely low frequencies, through microwave frequencies, including radar and optical light experimentation. We have a unique, very high power HF transmitting system, which is capable of temporary ionosphere modification for radio science research. We have a comprehensive diagnostic instrumentation suite on site at various science pads, as we call them, which includes, as a sample, magnetometers, rheometers, radar imaging systems, receivers, ionospheric sounders, so we can look in real time what the layers of the ionosphere are doing and what the MUF is. We have satellite receivers, general purpose receiving systems, arbitrary waveform generation, reception for digital modes, etc. We can do it all. Receiving diagnostic instruments on site typically run 24/7, collecting valuable long-term observations of the electromagnetic spectrum. The large HF transmitter only runs when we're in a research campaign. The facility is located in a region where the auroral oval, which is that concentrated ring of ionosphere about the North Pole, and also a similar ring about the South Pole. So we're in a region where this auroral oval of concentrated ionosphere and mid-latitude ionosphere are within our beam pointing angle, or view as we call it. It's an optimum location for most radio experimentation involving the ionosphere. The remote location in Alaska provides a wealth of research opportunities with low man-made electromagnetic noise levels and very low probability of causing HF radio interference to any service because we're primarily beaming vertically. And so it's an NVIS. Most of that energy comes right back down in the state. So just a quick, I'm not going to go through this entire slide, just a quick timeline of the history of the HAARP facility. In 1990, the program was funded by Congress to establish the state-of-the-art DC to light radio science research facility. In 1993, construction began, and we started off with 18 towers. And in 1994, we got the 18 towers going. We had to invent a lot of technology here, so it was a slow start to prove that we could build it and meet all the specifications. HAARP's first light, when we started transmitting with only 18 towers and transmitters, was 1995. By the time 1999 rolled around, we had learned a lot. We put up 30 more towers and built additional transmitters for a total of 48 transmitters, 48 towers. And we operated at that power level and did a lot of science, very successful science. And then in 2003, the program was going so well and working so well and good data coming out of the research that they decided to go to its full size. So that was fully funded. And in 2003 to 2007, we installed the additional towers, transmitter shelter buildings, and built the additional transmitters, which we'll talk about. And in 2007, we built the full array, which was 180 towers and 180 transmitters, and got all that up and running. And in 2013, we had that 9-month shutdown due to the politics of money. That's all it was. Very reckless indeed. But by 2015, the University of Alaska had taken over the project, and they do an excellent job running it now, the Geophysical Institute out of their Fairbanks campus. In 2017, the first major research campaigns were run by the university. In 2021, National Science Foundation provided significant funding and created the Sub-Auroral Geophysical Observatory, or called SAGO, with HAARP as the central component. And in 2022, we started giving public open house tours again, which we do every 2 years. So let's go north to Alaska. And where is HAARP? Well, here's the state of Alaska. You see Anchorage down here in the bottom center corner here on Cook Inlet. HAARP is located near the town of Glen Allen, Alaska, in the little town of Gakona. And that's about 200 miles east-northeast of the Anchorage area. This was the former site of a planned but never built HF over-the-horizon backscatter radar site. This was going to be the transmitter site during the Cold War. But by 1991, the Berlin Wall had come down and the site was no longer needed, so we grabbed a hold of it and built HAARP. We're in a permafrost area, which has significant impacts on construction methods, timing, and costs. We have to anchor our towers and buildings into the permafrost using thermosiphons, which I'll talk about. Only stable soil we can get to. And this location, as mentioned, provides a wide variety of ionosphere and space conditions that open up a wealth of research opportunities. And this picture to the right here, you see a small little section of the HF transmitting array. And you can see that's a real picture. That's the aurora painting out that auroral oval sitting right over top of us. And you can see the light on a dark night there. Okay, let's look at the HAARP site. This is our intermediate size here, and this is the full build out that exists now. On the far left here is the Copper River, where the famed Copper River red salmon come from. This is the Toke Road, Route 1, going to Canada. Canada's about 140 miles away. This is our operations center, a diagnostic radars scientific pad, as we call it. Here's the big HF transmitting array. That's a grid of radio towers, 80 feet tall, and it's a 15 column by 12 row grid of radio transmitting antennas forming a planar phased array. And there are these little white buildings are called transmitter shelter buildings. There's 30 of those, and each has 6 20-kilowatt transmitters inside. This is one instrument at the site. It's a transmit only HF instrument here. Total input power, 20 kilowatts per transmitter times 180 transmitters. That's 3.6 megawatts of input power. In the HF band, 2.8 to 10 megahertz is our operating capability, never in the ham bands, only in authorized spectrum. And the effective radiated power given the gain and the focus of the array tops out at 10 megahertz, the high end of our operating capability. And that effective radiated power tops out at 5 gigawatts. So it has quite a bit of gain, and we can electronically steer the beam, but that's our largest instrument. We have other roads here. We have an HF test facility with a lot of HF antennas, transmitters, receivers, aircraft alert radar we'll talk about, and more diagnostic pads here for various research instruments. Okay, so HAARP is a research and development instrument or site to advance the radio science art in our understanding and use of the ionosphere as a focus, but not as its only capability. So it has the unique capability of using the ionosphere as a nonlinear active medium. The HF transmitter can thus generate secondary radiation sources at ULF, ELF, and VLF rates, visible light, and IR light. It can also produce radio wave propagation effects and new signal paths spanning pretty much the entire HF spectrum, all by excitation of the ionosphere with our large transmitters. We all know the radio spectrum here. The key is that HAARP has the capability of transmitting. We can actually push it down to 2.6 megahertz to 10 megahertz. This is where we can transmit. But using waveforms and modulation, we can experiment and generate secondary emissions at ULF, ELF, and VLF rates. We can also experiment with propagation enhancement. We can also do propagation enhancement in VHF, UHF range, and also we can create optical effects, which is a great area of study. So emerging high-power radio technology for next-generation DoD systems, spanning 15 orders of magnitude of the electromagnetic spectrum. We have capability DC to light. Okay, this is sort of an interesting chart here. And what I'm showing you here is, one, HAARP is not the only ionospheric research facility with high power transmitters in the world, but it is the most capable by far, by any measure. So this left axis here, just to compare with some of the other facilities that are operating in the world, this is effective radiated power. That's the power in our focused beam width in dBW, dB above a watt. And here's HAARP at its current size. Oh, the bottom axis is frequency capability, not that we never transmit in the ham bands, only in authorized bands. We have an FCC experimental license. But here's just the general capabilities. So here's our ERP versus frequency range. So you can see the 2.6 to 10 megahertz here. Now there's a site in Norway called ISCAT, and it's in Tromsø, and they have this ERP versus frequency capability, and they're doing similar research for the Europeans. In Russia, they have a site called Sura. It's a very crude site, but it does have high power transmitters. It has a bunch of telephone poles with cage dipoles, and it's doing similar work, but their ERP is much lower and their frequency range much more limited. They also don't have anywhere near the technology that we have. Now, Arecibo used to have a 3-frequency ionospheric HF transmitting site that was on the coast of Puerto Rico. It kept catching fire, and eventually a hurricane took it out, so that's gone. There was a site up in Fairbanks called High Pass. UCLA ran it. That's gone too. And here the yellow line is HAARP before the final build out, when we had 48 transmitters. You can see the ERP enhancement there. So HAARP, so there are really 3 sites now. There's HAARP There's Tromsø, Norway, and Sura in Russia that are doing this ionospheric research. I'm going to go from the antenna down into the transmitters. It's the easiest way to tell the story. So again, the HF transmitting site, a 12 row by 15 column grid of phased antennas to form one or multiple beams that we steer electronically by phase. But let's talk about one of those towers of the 180. The tower is at ground and it supports dipoles. Now, if we go from the bottom up, we have to anchor into the permafrost. It's the only stable soil we have, which is always frozen because of the Alaska cold in the wintertime. So we have a 30-foot hollow pipe with a radiator arm that has 500 psi of CO2, carbon dioxide. During the summer, it doesn't do anything. In the wintertime, it's a passive system that when the fins get chilled by the outside air, that can go to 40 to 60 below zero Fahrenheit, but it starts working at 10 below zero, which is very common in the wintertime for 6 months or more. It chills the CO2, it drips to the bottom, and down in the permafrost crust here, we're anchoring to, it's about plus 29 degrees Fahrenheit, so it turns back to a gas, and it just keeps doing that, and it sucks heat out of the ground and super freezes us into that stable permafrost crust. That's called a thermosiphon. All towers and our buildings are mounted on these for stability. We come up 15 feet and there's a ground screen. It's an 18-inch square AlumaWeld ground screen grounded to the towers. That's a reflection ground plane. So our shelter buildings, vehicles, and people are under the ground screen. So this is a flat reflective ground screen because we want to be a quarter wave off the ground screen for reinforcement back up. So here's a set of high band dipoles. This is one high band dipole, what we'll call our north-south, with a matching unit, trying to be a quarter wave off the ground screen, and this would cover 7 to 10 megahertz. When we go lower in frequency, we switch to a three-dimensional fat bow tie dipole. That's obviously longer, and it's higher up off the ground screen to get back to a quarter wave for that reinforcement reflection up. It has its own matching unit, and that covers 2.6 megahertz to 8.1. There's a little overlap, and we switch between the two dipoles depending upon what band we're in. Now, I said, imagine these as north-south. We have crossed dipoles at 90-degree angles, so there's an identical set of dipoles coming in and out of the screen from the same point, which you'll see. And that's done so that we can create circular polarization. We can, by phase, we can have circular right, circular left, have to have cross dipoles to do that, or we can do linear or elliptical. It's a user choice. And so the towers here are about 80 feet tall. Okay, here's a picture of what I just explained to you. Here's that thermosiphon, that white pipe there, a steel pipe. It's just a hollow pipe 30 feet down in the ground. Here's the radiator arm and the fins. During the summer, does nothing. During the wintertime, it's this 500 psi of CO2 gets chilled and into cold water droplets. It drops down, plus 29 in the permafrost, turns back to a gas, comes up and repeats. It's sucking heat out of the ground, super freezing us in an ice ball into the stable permafrost crust. As we come up, you see the base of the tower. Here's some RF distribution heliax lines, fire alarm, and fiber optic LAN. Here's the ground screen. You can see the ground screen up here. It's an AlumaWeld crimped ground screen, 18 inches square. You can see it up here. And that's 15 feet off the ground, grounded to the towers. And as far as RF at these wavelengths, that's a solid flat metal plate. Then we come up the tower. Let's go to the left side of the picture. You see two of these round cans. Those are antenna matching units. And there's one for the east-west dipole and one for the north-south. Those are high bands. And then we go up higher with these metal booms, and there's a three-dimensional wire cage. And again, east-west, north-south matching units for the low-band dipoles. And again, the towers are at ground. These are the shelter buildings, custom built for the transmitters. They're air-cooled. There's 6 20-kilowatt transmitters per building, and there's power distribution transformers to get 480 into the shelter. Nobody has to be out in the array when we operate. It is done 100% remote over a local area network connection, and everything can be turned on, turned off, and operated that way. Okay, let's zoom in on a tower here. Up at the top of the tower, of course, to get that quarter wave at the lowest frequency, longest wavelength, we have our crossed low band dipoles. There's an insulator here, and this is 1/2 dipole. The boom is part of the radiator, but there's also, it's hard to see here, but there's a 3-dimensional fat bow tie cage that's all shorted at the end to lower the Q. So here's one, we'll call this the east-west dipole. You can see my pointer moving back, and this would be the north-south dipole. So there's a matching unit here that takes a 1 5/8 corrugated heliax coax, solid foam dielectric, no air in it. And that's our main feed coming in. And then go lower on the tower. These are the 2 high band matching units, one for east-west, one for north-south. You can see one dipole down here. Here's 1/2 of a dipole. It's 3 wires in parallel that go and get shorted on the end. Now look at these square boxes here. Each matching unit is paired with what's called a dump load, larger dump load. So this dump load is for the opposite face matching unit. This one is paired with the other one. At the high band, which is 7 to 10 megahertz, the dump loads are bigger. Those are convection cooled 50 ohm loads, and their only purpose in life is if through mutual coupling by physical proximity, we get RF from other neighboring towers that's in what's called the even mode, where the voltage polarity is the same on both sides of the dipole. That power physically can't radiate, and it's an artifact of mutual coupling by proximity in the array. We have to do something with that power because it's going to want to return back down the transmission line into the transmitter, and we'll get RF all over the place when we have these hot spots of even mode mutual coupled power. So our antenna matching unit has a dump port, and if there's even mode power there, it'll just dump it off as heat because we can't use it. But most of the time it's not there. It moves around in hot spots. So those are what are called even mode dump loads. So again, we have 2 sets of cross dipoles, low band 2.6, this says to 8.4, and 7 to 10, fat bow tie geometry. Everything's welded, and the ground screen is welded or crimped, designed to survive 100-mile-per-hour winds. Okay, this is what an antenna matching unit looks like. We designed this in our office. This is very unique. There's no motors. It's all fixed tuned, but the input power comes in here, and there's a 1 5/8 EIA flange connector, 50 ohm, standard in broadcast. And again, we're using 1 5/8 heliax cable cut to an electrical length for all towers. So that comes in, and this is 2 different tape wound Teflon double shielded silver plated coax from Times Wire, specially made for us with this jacket. And this is a 4-port hybrid transformer, a TEM mode transformer. And so this transformer gives us the Balun function very well. It gives us a broadband impedance transformation like a transformer can. And it also gives us that even mode power dump port, which is this tap coming here to this 716 DIN. If that even mode power, an artifact of mutual coupling by proximity, that is power in the even mode that physically cannot radiate, we have to deal with that. And so we just dump it off as heat if it's there, and it's just hot spots that move around. That was something we had to learn when we built the site. There are spark gaps on the balanced outputs and vacuum relays that we open when we're going to another band, some silver plated coils, and a vacuum cap. The total insertion loss at worst case load impedance is 0.2 dB, and it's inside this can that's pressurized once with air. And that fin at the top is just a heat sink. That was a high current point. Okay, let's look at the transmitter buildings here. These are specially made buildings for us. They're not just simple trailers. As you walk in a transmitter building, and I have a door open in the back there to let some light in, the first thing you see on the left is a control rack for the phase control and monitoring and networking of all the transmitters. They're all operated over a fiber LAN, local area network. There are 3 transmitters on the left, 3 on the right. These are air-cooled transmitters. So back in the back corner behind this door is a blower, a huge 3-phase electrically powered blower, and it charges a plenum that's in the floor. And you can see the outlines of a hatch under this mat here. But whoops, there is a plenum in the floor with holes cut. And so there's one blower charges the floor plenum, an insulated plenum, and it shoves cooling air up through the transmitters. Then these black hoses at the top that you can kind of sort of see from the tube stacks take the hot air and put it into a return plenum that's in the ceiling. And we automatically mix the hot return air with the incoming cold air from the outside to maintain 55 degree Fahrenheit inlet air temp. So this is all the transmitter sheltered buildings are this clean, this nice. And these are 20 kilowatt each transmitters. They have a Continental nameplate, although 50% of the transmitter was designed in our office, the software, the low-level RF, the modulation, and the tuning. Continental out of Dallas did the tube deck, the high voltage power supply, the tuning coils, and the final assembly and test. And we have 180 of these, 6 per transmitter shelter building. And here's a shelter building from the outside. You can see the coaxes coming out, going to their towers that are around the building. So again, 2.6 to 10 megahertz continuous tuning. Each transmitter has dual independent outputs. This right side is a 10 kilowatt independently tuned amplifier for the tower that's married to this transmitter. And that would be the right side is always the north-south dipole on that tower. The other side is another independently tuned 10 kilowatt transmitter or amplifier, and that is for the east-west dipole. So each transmitter is a dual 10 kilowatt transmitter. Not much of a front panel, just some watt meters and breakers because we use a laptop plugged into a switch to log into each transmitter and get a software control panel. So dual independent outputs, 10 kilowatt each side. There are 4 IMAC 4CX 10,000D tubes per transmitter. Well, why 4? Well, there's 2 IMAC 10,000Ds in the north-south power amplifier in grounded grid, cathode-driven push-pull operation. But then we have 2 more in the left side for the 10 kilowatt amp for the east-west. So that's a total of 4. Everything before those tube finals are solid state. We have a solid state broadband 1 kilowatt driver in the center drawer, and down here in the bottom exciter drawer, we have a 50-watt amplifier and our digital exciter for each side. We have automatic antenna tuners at each 10 kilowatt side that can tune to a 5-to-1 VSWR. We have graceful degradation above 5-to-1 VSWR. These are linear amplifiers with a 200 kilohertz bandwidth. That's huge. We don't need anywhere near that. We're generally not wider than 50 kilohertz and usually much more narrow with our waveforms. But at 10 megahertz, that useful bandwidth actually goes up to 500 kilohertz. So very broadband transmitters, but we don't need or use that much bandwidth. The harmonic and spurious is extremely low. In band up to 10 megahertz, minus 80 dBc for harmonic and spurs. Out of band above 10, we're minus 120. And from 88 to 200 megahertz, where there's broadcast and wildlife tracking, we're minus 150 dBc, one of the cleanest transmitters ever built. Modes of operation, CW, AM, FM, phase mod, pulsing with shaped rise and fall times. 6 dual units, dual 10 kW transmitters, or 6 20 kilowatt transmitters are mounted in each shelter building. And we have 30 of these buildings. Now, the reason why we have 30 of these buildings is we need to space the transmitters out. So we're using a constant length, a constant electrical delay of RF feed line to the towers that are on either side of a building. And since all transmitters have the same electrical delay in their feed lines, because they're straddled by the towers, they're energizing, that's a constant, and we can now ignore the transmission line delays. Okay, so here's the operations center. This is where the operator sits. Here in the center, status screens up at the top, the control screens in the center. monitoring equipment here on the right, two-way radios and power plant operation here. This is environmental controls, aircraft alert radar, and the experimenting scientist will oftentimes come and sit here with access to a PC so he can talk directly to the site operator. We do operate the site remotely over the internet, although for the larger research campaigns, it's much better for us to be on site to have better situational awareness, but we do operate it remotely. All waveforms that we transmit are generated in software and sent digitally via a fiber optic LAN to all the transmitters. Okay, how do we keep track of this many transmitters? Well, if you were a bird and you're flying over top of the HAARP site, this is geometrically correct for towers and for shelter buildings. Let's go up to the top left corner here. If this is north facing up, and this is the northwest corner, this is the shelter building that's off in that corner. That's the first one. We call it shelter A and shelter A1 is what the shelter, and you walk in and those are the first three transmitters on the left. These are the three transmitters on the right, and they're straddling towers that are in the same geometry. So this is absolutely geometrically correct. So this is one of the many displays we have. RF means the transmitter's on. Let's zoom in on this first transmitter here, and we have a column row nameplate. So this is transmitter 0101, column 1, row 1. This next one over would be 0201, still row 1, column 2, and so on. So each one has a number. So this is transmitter 0101. RF forward power is green, reflected power is blue. This is a real-time display that we see when we're operating. RF means it's on. Up and down is the north-south 10 kilowatt amplifier. Left and right is always the east-west. Green is forward power, blue is reflected power. So rather than having two bar graphs that are thin and at a right angle, we just force them to form a box. So the reflected power is on top of the forward power. Hopefully it's less than the forward power. And this is a log scale, so that's one box down for north-south. So that's a 2-to-1 SWR, 10 dB return loss. And then for east-west, we're just forcing the reflected powers to form a box. And so it's easier to see. And that one's got a little bit worse than a 2-to-1 SWR. But the fact that the green is all the way up means they're at full 10,000 watts. So these A's here in the middle, these are transmitters that are out of service. We never see this, but in the early days, we were working out some kinks. But A means antenna band open, vacuum relays and the matching units are open, so no RF gets shoved down off transmitters. So we're floating the half dipoles. And that's what the A means. And this one's off. It's yellow here because some meter readings and warning. This one's off and this one's off. So this is 180 transmitters. Up and down for each one is north-south, left and right is east-west. And there's various other colors here. Now, if a transmitter goes into warning, it'll show yellow here. We can click on this with a mouse, bring up the control panel for that transmitter, see what meter reading is in red, and work on it, fix it, or understand what's going on. Very novel way to show 360 10 kilowatt amplifiers or 180 20 kilowatt amplifiers. Now, we can assign a color temperature to any data item we like. The maintenance people love this. So here I've assigned a color temperature to forward power and reflected power. So for east-west, we call that PA1. Here's 180 east-west amplifiers with their row column. There's our 0101, and it's showing 10.0, so it's putting out 10,000 watts. His reflected power is right here, and his reflected power is showing 2.7 kilowatts. So he's a little warmer. These are colder, meaning lower values. And so this one corresponds to this guy. This one here corresponds to this guy down here. So the white ones are the ones that were off in the previous display. But oh, look at this one down here in the bottom center. That's much warmer. in our color scale, that means the value is much higher. It's an outlier. That's how this is valuable. 4.6 kilowatts reflected for 10.3 forward power. There's a problem with this tower that needs to be fixed. That's too high. So we can do this for air temperatures, driver power, driver reflected, 483 phase current, whatever you want. You can bring that up as a color temperature graph, find the outliers, and go fix things before they fail. Very powerful. Okay, we also have a unique capability at the site where at the balanced outputs from all of our matching units on the towers, we have a current monitor, a little transformer that takes a few watts of sample off the dipoles, and we bring those back into the shelter buildings, do an A to D, and bring back dipole current samples, excuse me, where we get real-time dipole current amplitude, frequency, and phase. And we put that into a NEC4 model of the array and calculate our pattern. So here's a display here. This is kind of looking down on the top of the pattern. We're beaming vertically up. We can steer the beam in a plus or minus 30-degree cone. Here's a side view looking at, and this is our actual radiation pattern using real-time measured dipole currents for every dipole, and then we can calculate the radiation pattern. And this was verified as very accurate by airplanes that were flown in the far field and measured our pattern by the government. Here's a standard display like we just looked at, all 180 transmitters up and operating normally. That's what we normally see. And this is a display of impedance of each dipole using a color temperature graph. So we have enormous measurement capability for this transmitter instrument to give the scientists exactly what they want. Whoops. Now we can also split the array arbitrarily into two different frequencies, doing two different things simultaneously. We have dual frequency capability. So in this example, here's the radiation pattern. This guy's got more ERP than the green. So who is that? Well, that red is at 6.8 megahertz. It gives us our beam pointing angles, 4.702 megawatts, and the gain of the array is 24.705 dB. And this is a simultaneous transmitter with the balance of the remaining transmitters, at which they assigned a 4.5 megahertz. There's the beam pointing angles, 2.573 megawatts, and the gain of the array for those chosen transmitters is 21.56 dB gain. So again, the scientists can split the array arbitrarily and have two completely separate things going on if they want, or they can put the entire array on one frequency only and get the maximum ERP. Extremely versatile. These can be different polarizations, circular right, circular left, linear, elliptical. It's just an operator's choice. Okay, how do we power this site? And then we're going to zoom in on the transmitters. The local power utility comes out of Valdez, Alaska, which is 150 miles to our south over a major mountain range. We do get three-phase power. It's only good for 600 kilowatts, not nearly enough. So we have our own power plant, which is 5 20-cylinder EMD locomotive diesel engines, turbocharged, compressed air start, all operated with a mouse. Each one is good effectively for 3 megawatts each, and we have 5 of them. So we have a 15 megawatt power plant of our own. We only need 4 of the generators on to run the array. You can see the pulse rated generators here in this view. They're auto syncing, compressed air start, as I mentioned, run by a mouse. And so the power plant uses 5 EMD diesel engines, each of which is rated at 3,600 horsepower. The total power generation capability is 16.25 megavolt amps, or if our power factor is not this bad, but at 0.8, it'd be 13 megawatts. With that low power factor, ours is much better than that. That's much closer to 1. To operate the array at full power, we need 4 of the generators on, which is about 10.4 megawatts. To give us a little headroom. Fuel consumption at full array power with a CW carrier is 500 gallons per hour. That's quite a bit of fuel. Our transmitters are only 42% efficient because they're optimized for low noise, ultra low phase noise, and high linearity. And it says 1.25 MVA of commercial power. It's really about half that. which is hydro out of Valdez, where we run the offices and science pads from. Okay, the FAA came to us and they said, can you guarantee us that you will never, ever be a hazard to flight? And what does hazard to flight mean? Well, what that means is if they flew through your transmit pattern at these very high ERPs at HF, would you disturb a navigation instrument? Maybe, probably not. Or would you blank out the front end of an aircraft radio and they would miss an important radio call? Maybe, probably not. But anyway, we can't say anything 100%, and we don't want to get blamed for anything that we didn't do. So what we proposed, and they love this, is we have on one of our science pads, we have this aircraft alert radar that has to be operating when the big transmitters are on the air. And what it is we have 3 different inputs to track airplanes. And if we see an airplane come within 5 miles of the site, we automatically stop transmitting, and it's done in software. We get a beautiful radar display with radar tracks from all 3 sensor inputs, and we stay off the air until that target is either coasted or tracked to be more than 5 miles away, 500 feet to 55,000 feet. So how do we do that? Well, we have a 30-foot Roan 55 tower here. That's a 60 kilowatt S-band Furuno maritime radar with this antenna pointed up to get mainly just the low-flying bush planes that don't have transponders. That works great, beautiful tracks. And then we have on this shorter tower, we have a TCAS, the collision avoidance system, a high-power TCAS that airplanes use to ping Mode S transponders, the old style. And if a plane is going to come too close to you, it'll automatically make one plane go up and the other go down. Well, we're not a transponder, but we can ping transponders. And this gives us a hemispherical pattern, so no cone of silence above us. And we get beautiful transponder tracks out of this TCAS unit here that's walked up and down in altitude. So that's a secondary track. And then we have the new latest GPS-based ADS-B receiver on another science pad that also tracks the beacons, the ADS-B beacons of planes. So we get 3 tracks, and when a plane comes within 5 miles, we automatically shut down and we don't come back on the air unless it's perfectly clear. And if we lost a target, we'll coast it out and then we'll come back on. So the FAA thought this was brilliant. They loved it, and we could never be a hazard to flight because we automatically shut down. And this has to be on or we don't operate. Okay, so transmitters. We designed half the transmitter in our own offices. I was the lead designer. And we then worked with Continental to do the cabinetry, the tube deck, the tuning coils, and the high voltage power supply for the tube finals. We did everything else, the software, the digital, the networking, the exciter, the modulation, the metering, the controls, everything else we did ourselves. They were our manufacturer, and I did all the acceptance testing down there, and they built 180 of these. So here we are installing a brand new transmitter. We installed them all ourselves. Continental never came to the site. So we installed them all ourselves. So here's 3 of the site engineers rolling a new transmitter into a brand new shelter building. Here we are after doing QA on a transmitter hooked up to this 1,300-pound 3-phase power transformer, 480 3-phase coming in. Gives us all the high voltage 3-phase taps for the plate voltage and the screen voltage and so on for both sides of the transmitter. Here are those RF outputs for this would be the north-south side. This is a 1 5/8 EIA flange, a 50 ohm connector used widely in broadcast. So we have the antenna port here and a dummy load port here for test and calibration. This transmitter is getting ready to be slid back to the wall and bolted to the floor. Here's the cooling air coming in from that floor plenum. For this side of the transmitter, cooling air for the next. It has neoprene tape around it. So we're pushing air up through the 50-watt amp down here, through the 1 kilowatt driver that runs normally at 500 broadband here, and then through the push-pull pair of tubes, and then out the top. Here's another transmitter that doesn't have its back panels on. This is an output tuning coil for the antenna tuner. This is actually a rectangular coil with sliding contacts and a stepper motor that drives it. Very rugged, silver-plated brass rods, but these diagonal bars make a rectangular coil, and we can adjust the value with the stepper motor. But this is the next transmitter that'll get pushed back. So here's kind of a front and a side view. So this is one 10 kilowatt amplifier. This is on the right side. This would be north-south. These are 4CX 10,000D IMAC tubes. We're 100% IMAC. There's two 10,000Ds in push-pull. The plate voltage is nominally 5,000 volts, screen voltage 800 volts. The grid voltage is adjusted for a Class AB idle bias of 550 milliamps in the tube. They're in grounded grid for unconditional stability, cathode driven, in a push-pull pair. Now they're in a push-pull pair because we needed to bury our second harmonic and the even ordered harmonics. And I have 20 kilowatt, 10 plus 10, 20 kilowatt of plate cooler to waste off heat when I get pulled out of tune, which we have to do. These are the two vacuum capacitors for the plate tank tuning. This is the plate coil here. Same concept, stepper motor driven, diagonal shorting rods. There are beryllium copper springs that ride on these rods, and this moves up and down. The air stacks are not in here, so you can see everything. And here's a side view of this same cabinet here. Here's the side view of this plate coil. You can see the stepper motor here with a bellows coupler. This big vacuum cap back here is part of the antenna tuner, and this is the output coil for the antenna tuner. Again, stepper motor drive. Here's our right angle miter, 1 5/8 EI flange. Here's 1 5/8 coax built to a specific electrical length going out to its tower, solid foam dielectric. Okay, here's what the exciter drawer looks like. Now, this was built in the mid-90s, but this is a digital exciter modulator, we call it. Very state-of-the-art, even to this day. It's state-of-the-art, designed in our office, and it can do AM, FM phase mod, and pulsing with user-defined rise and fall times. Very high precision power measurement as well. This board back here is what we call our DC meter board. It's the main interface to the transmitter itself. And here's our 50-watt amplifier here, which drives the 1 kilowatt. Here's our high voltage power supply here. This half goes to the east-west 10 kilowatt amp. This half goes to the right. So again, this is the bottom drawer open, digital exciter, and precision RF measurement board, 50-watt amplifier, typically runs about 20 watts. And here's the center section HV for the tube amp. Those are oil-filled caps. And again, we're nominally at 5,000 volts on the plate. Okay, so here we are mounting transmitters in a shelter building. Again, power transformers get mounted first, 1,300 pounds, pulse rated. Here's a transmitter that's been pushed back after QA. They're pushing another one back. We can do all the maintenance we need from the front and the side, no problem. You see the high voltage power supply in the middle here. Again, the left side is a 10 kilowatt independently tuned side. That would be the east-west dipole in his tower. This 10 kilowatt side is independently tuned, generally to the same frequency as the other side, but this is tuning to the north-south dipole. Bottom drawer is about 20 watts operating. Center drawer is driver, nominally 500 watts. Tube push-pull pair here is output at 10 kW. Power meters, breakers, and we plug into a LAN and talk to them and get a beautiful color control panel. Okay, so here I am calibrating a transmitter. We pioneered a calibration technique where we actually calibrate every single one of these transmitters to have precision close to a piece of Agilent or Hewlett-Packard or Keysight, if you will, test equipment. We do a tuning cal. We sweep the transmitter with a network analyzer, and every 500 kilohertz, I precision tune with stepper motor offsets for perfect gain, phase linearity, and bandpass shape. Save that off every 500 kilohertz. And then I do a precision power cal into dummy loads at various power levels. every 500 kilohertz, and then the software does a spline fit interpolation between these cal points. So every transmitter gets perfectly calibrated, has its own cal file, and ultimately we get precision that is not quite as good, but close to a piece of professional test equipment. And the scientists demand that. You can see 3 transmitters behind me. You can see the air stacks for the hot air. Here's the tube stack for the hot air coming off this tube. We do measure to make sure there's airflow, or the transmitter will shut down if it doesn't have enough airflow. We use 1,500 linear feet per minute per tube, plenty of air. And we also have a temperature probe, a thermistor, so we can continuously monitor airflow and the stack temperature to make sure the tube finals are happy, in addition to voltages and currents on the tube. Okay, here's what a finished transmitter shelter building looks like at HAARP. Again, there are 30 of these buildings. They are this clean all the time. And so we have 3 transmitters on the right, 3 on the left. You can see the little Jesus stick here that we use to short things out when we do maintenance to make sure there's no stored energy. These are QA sheets after inspections. They're not normally there, of course, but this one just got its final inspection. This rack here has phase control, current monitor, A to D, networking, and single phase ups, and that's sort of thing. And again, that single blowers back in the left corner. The floor is our supply plenum, blasting cooling air up through all the transmitters. The ceiling, you see these black hoses, that's where the hot air comes out, a common return plenum in the ceiling, and the shelter control systems automatically mix the hot air with the incoming cool air from the outside to maintain a plus 55 degrees C inlet air temp in the supply plenum. Again, everything's operated over a fiber LAN. You can come out here and look at this stuff when it's running. There's nothing dangerous, but there's no need to be out here unless you have to be. It can all be operated over the LAN. So this is from about 1,500 feet up. Here's the big transmitting HF array. That's 33 acres, 180 towers, a 15 column by 12 row grid. This is like a lens where we can form that single beam and steer it around rapidly or slowly or fixed pointed in a different direction. Our primary design space is plus and minus 30 degrees from vertical. We can push it lower, but our side lobes come way up and our back lobe starts to come up. But the official design space is plus and minus 30 degrees from vertical in a cone. And you see this is Mount Sanford in the background and the Wrangell St. Elias. This is not Denali. That's way too far away. But that's about 25 miles away, and that's about a 16,000 foot mountain peak in the Wrangell St. Elias Mountains. You see our operations center here, and that low bay is the generator bay. There is a soundproof wall. We have 15,000 gallons of fuel storage on site above ground. Diesel fuel is Arctic grade, so it does not gel when it gets 40 and 50 below. So we don't have to worry about that. And this is our ionospheric sounder here. This is our satellite pad and where the sounder equipment sits. And there's another radar, an incoherent scatter radar, and other instrument science pad here. So that's a 33-acre phased array. That's just one instrument, but our biggest, and that's the big HF transmitting array. Okay, here's a picture I took when I came in one morning with hoarfrost on everything. Again, you can see the ground screen frosted up. You can see all the Philly strand guys, all the guy wires. These are guide towers. The guys above the ground screen are all Philly strand, non-conductive. Below the ground screen, it transitions to steel, a wire stub to go to another tower brace, and they're tensioned and trued, the towers and the guys. And you can see the low band and high band matching units and their associated even mode dump loads. Okay, so let's talk about the auroral oval just a little bit. The Earth's magnetic field pulls the ionosphere down closer to the Earth in a ring about the North Pole and the South Pole. And there are satellites up that image this auroral oval, and it's known for causing the polar flutter that we hear on single sideband and AM when signals are going over the pole. And here's another satellite observation of the auroral oval. Again, it's a concentrated hollow ring of ionosphere that moves. It breaks up into multiple ovals sometimes, but it's a ring of ionosphere, and we use that to ping it basically with our high power RF for experimentation. And when it goes too far north, we get mid-latitude ionosphere. Here's a picture. I did not take this picture, but this is a picture from the HAARP site. This is our optics trailer. We do a lot of optics work, and it's open and currently making observations. But here's the Aurora Borealis right over top of the HAARP site, and it's painting out that auroral oval. The Aurora Borealis, is caused by energy from the sun being pulled down into the more dense atmosphere and causing molecules of nitrogen and oxygen to give off light. And on a dark, moonless night, you can see it, and it is this brilliant at times. So again, it shows the HAARP site being positioned under the auroral oval painted out by this visible aurora. Okay, so let's talk about using the ionosphere and what some of our experimentation is. So if I came to you as radio amateurs and I said, look, I want you to build me an antenna for RF at 100 hertz. Well, the transmitter is not that big of a problem. But what is a problem is the antenna. The wavelength would be over 300 miles long. And to get a useful radiation pattern, you'd like to be a quarter wavelength above ground, if not a half wave. And that's way too high up. You'd never be able to build a tower that tall. So the problem with ELF and VLF, which we define as under 20 kilohertz, is you can't build a good antenna to transmit it. But you would like to have one because you'd like to have some bandwidth to put some information on that. So what HAARP can do, and this is sort of rooted back in the old Luxembourg effect that was discovered in Europe back in the high power broadcasting days on AM radio. But there's a technique where, in this case, HAARP can beam up in HF, let's say 6.7 megahertz. They like to be just below the vertical incidence MUF, maximum usable frequency. So we look at our sounder, we see, okay, vertically sounding, what is the vertical incidence MUF? By the way, the vertical incidence MUF rarely goes above 10 megahertz. The oblique or low angle MUF can go up to 30 megahertz, as we know. But when you're beaming vertically into the ionosphere, the MUF never goes that high. So that's why HAARP is only capable with its transmitters in this arrangement to go to 10 megahertz, because the MUF rarely goes higher than that. And they like to be right below where the MUF is. And in one of the circular polarizations, I can't remember which one is the most absorptive, right below the MUF at that moment. So they'll look at the sounder, figure out what the vertical incidence MUF is, find our closest operating band, and then they'll generally go to the circular polarization, although it could be linear or elliptical, whatever they want. But then they can put, as a simple experiment, a 100 hertz square wave, 100% AM. So my ERP is going up and down, basically, in this simple example, at 100 hertz. And that modulates the currents that are flowing in the ionosphere. So natural currents flow in the auroral or equatorial ionosphere at this altitude. The HF signal interacts with the plasma conductivity. The electrojet current is caused to vary at an ELF-VLF rate by our high HF power. So we're basically stimulating the plasma of the ionosphere at our modulation rate in this example of 100 hertz square wave. If you had an HF receiver, it'd just be a low frequency tone you would hear. And then what that does is that causes a secondary emission of useful coherent RF at our modulation rate. So we can stimulate out of the ionosphere useful RF at our modulation rate. In fact, we can chirp our modulation rate from less than 1 cycle per second all the way to 30 kilohertz, and we can get RF back out of the ionosphere instantaneously over that full 30 kilohertz bandwidth. It's amazing. It's not strong. It's actually rather weak, but it's enough. It's enough to play with, and they're trying to optimize the efficiency of this process. And so here you see the radiated ELF signals radiated, and it's related to the power of the HF transmitter. So why do we want this low frequency RF? And again, this is one of 1,000 things that HAARP is there to experiment with. We do communications, we do optics, we do deep space, we do ionospheric modeling and propagation and stimulated emissions. It's extremely vast, and there's no nefarious activity here, none. It's all above board, and it's not hurting or bothering anything. It has no effect on the weather whatsoever. So anyway, why do we want ELF VLF waves? Well, it turns out that the skin depth of soil and salt water is kilometers deep at these ELF rates. So here, HAARP can transmit pulsed HF with a modulation on it. We can get pulsed ULF, ELF, VLF coming out of the ionosphere, and we can then overfly a surveillance area, and we can get the incident wave and the reflected wave, and we can image what's underground, caves, tunnels, bunkers, complexes. We use a mining school north of us by about 90 miles in Delta Junction, Alaska, as a target of opportunity. And in that case, we hand walked a receiver over the top of this mountain where they teach people how to mine, and we image the mine shaft using ELF generated by HAARP in a pulsed mode. So and this is old data. This has been around for a long time. So that's just one of the many uses. It could be communications, it could be natural resource exploration, or caves, tunnels, bunkers, complexes. It could be communicating to submerged subs. All kinds of applications, but you need to be able to transmit the ULF, ELF first. Okay, here's an optics experiment. This is HAARP transmitting up into a dark sky, and it's this wide because the beam, of course, gets wider as the distance goes out. This, you could not see this with a naked eye. This is a high sensitivity CCD camera, but we can see the stimulated aurora, if you will, or light energy with a high sensitivity CCD camera from just HAARP, just transmitting an unmodulated carrier up into the ionosphere. And then as soon as we stop transmitting, it just goes away. It's not hurting anything, but there's a lot of optics experiments. The physics folks are working on all kinds of things. Okay, so what about radio wave propagation experiments? Well, we can create what are called wave ducts. We can create interference called scintillation on demand. So let's say you're a GPS receiver manufacturer, and your job is to develop algorithms to take out the distortion from transmitting these weak GPS pulses through the ionosphere. Well, you can't wait forever for the sun to do something to give you distortion to see if your algorithms can work. So we have satellite pads at the site, and we can create ionospheric disturbances on demand, so they can look at the distorted satellite waveforms and test their software to remediate or eliminate it to their heart's content. We can create all kinds of distortion and things. And we can also create mirrors in the sky called a field aligned irregularity. Just by transmitting a carrier, we can create a reflecting layer for VHF that's very effective and can enormously extend the range of VHF comms as long as our carrier is on and we create this structure in the ionosphere. This is just a sample of all kinds of radio science that are being explored and filling the physics journals and developing new products. So here are some examples of some of the research activity at HAARP. The National Science Foundation, as I mentioned, established SAGO, the Sub-Auroral Geophysical Observatory for Space Physics and Radio Science. We're the centerpiece of that. It will contribute to the research infrastructure of the United States, educate the next generation of space radio physics scientists, and encourages citizen science via the amateur radio community. We do make operation and announcements to the hams through ARRL, and we do work with the folks from Ham Sci and give them a lot of look into what we're doing. And we're forming a team with Ham Sci, and we have community outreach programs teaching science and engineering concepts. The goal of the research at HAARP is to conduct fundamental study of the physical processes at work in the very highest portions of our atmosphere called the thermosphere and ionosphere. This research falls into two categories: active, which requires the use of the Ionospheric Research Instrument, IRI, that's the big HF transmitting array, and two, passive, which only uses monitoring instruments. And I went through some of the examples of what's going on up there. We operate in what's called research campaigns. So most of the time, the transmitters are off because the fuel consumption is high and it's expensive to burn that much fuel. So the site typically doesn't operate more than about 18 weeks a year. It operates generally for 1 to 2 weeks at a time on a research campaign. Multiple experiments that are unrelated are time shared through each hour. The site software is beautiful. It runs automation scripts, and then we change frequencies every hour to follow the vertical incidence muff for best effect. But we only operate about 3 to 5 1 to 2 week campaigns a year, and then we have summer school up there for students to run experiments and learn, and we do short campaigns that are 1 to 3 days periodically. So most of the time the system's off and not operating. So it's very intermittent. We do monitor frequencies before we transmit and authorize bands. If we see any activity at all, we move, and we're in VIS anyway, so most of our energy is coming back down. It's not generally very strong outside of Alaska, unless we're pushing to a low angle for over-the-horizon backscatter radar experiments. But you can see some of the examples here. We're doing over-the-horizon backscatter radar work, the stimulation of ELF and VLF RF, improvement of ionosphere propagation models, generation of artificial air glow, HF propagation analysis modeling advancement, and RF signal propagation enhancement experiments, digital communications on HF, new waveforms and error correction strategies. We have this polar aeronomy and radio science summer school where graduate students come to the site. They run their own experiments. We study the ionosphere propagation distortion for satellite navigation and microwave communications to satellites. We can run in an HF radar mode for interior sensing of shape, density, and composition of near-Earth asteroids. And we do moon bounce RF signal experimentation. And so that's just a small sample. And to wrap this up, here's just a wintertime view of the HAARP site. Again, the array is quite large to generate that high ERP, 180 20 kilowatt dual 10 kW amplifiers, transmitters in a phased array where we electronically steer the beam. They can do any modulation you want, any pattern you want within the physics of the array. And it's all run over a LAN, super high signal purity, super highly calibrated. And this frost has no effect on it. So it's really a national treasure, and the site is active and working very, very well. And the radio science is just pouring out of it. We do have an amateur radio call sign for the site, and that's KL7, effective radiated power. We have a small ham station on the site. It's only 100 watts to an OCF dipole. We can't use the big transmitters for any amateur radio transmissions. And there's another wintertime view of the HAARP array. You can see the transmitter shelter buildings. Again, here's that ground screen, 15 feet above ground. And you can see the dipoles, the big three-dimensional cage dipoles for the low band. You can see the matching units. Again, one for east-west, one for north-south, low bands at the top, high bands lower down, those even mode dump loads for that even mode mutual coupled power that we can't do anything with. So we have to waste it off as heat. It's hot spots that move around the array, just have to deal with it. You see the thermosiphons at the bottom, and there's a vehicle out there in the snow. Somebody's in that shelter building doing some work. So anyway, that's a quick look at the HAARP site, and I barely made it to about an hour. And if anybody